Okay, so a few people have asked for another video for a compound interest formula. So I am looking at some problems from section 6.4 out of your textbook. So I'm looking at problems on page 290 to try to help you work through some of these interest formula problems. I think that part of the issue might just be a simple order of operations thing, because sometimes these are just tricky to put into your calculator. So let's see what we can do. So anyway, this is the formula for compounding interest right here. We're going to use this one a lot. One thing that your textbook mentions that you might miss is that this is for when we are compounding monthly, because we know that is true because of the 12 on the bottom. I'm actually going to bring that up here in this second problem because I don't think it does a good job of showing, your textbook at least doesn't do a good job of showing the difference in these two problems. So anyway, this first one says you deposit $1,000 into a savings account. The savings account earns 5% interest compounded monthly. Find the balance in the account after each time period. So I'm going to look at problem A first. Okay. That's right. All right, so I want to identify these things. So A is the balance in the account after so many years. P is the principal. R is the rate. N is the number of months. All right, so I'm just going to plug those things in. The principal is how much you put into the account. I'm just going to copy this again. So if we put in this account, we're going to put, we're going to put $1,000 into this account. So I'm going to, sorry, my mom's commenting on things. I'm going to put in $1,000. The rate is 5%, but remember we have to change our rate to a decimal. So 5% is a decimal, 0.05. And N in this case is the number of months. Don't be tricked to think that it's the number of years. Because in this case we're doing 10 years, but you got to think about how many months that is. So if there's 12 months in 1 year, if I multiply that by 10, it's 120 months. So I know most of y'all can do that in your head, but just to show you how I got that. All right, so here's my formula. So we're going to start to make her smaller. All right, that's what we always do, right? That's order of operations, is truncating things down. So I'm going to do inside the parentheses here first, and I'm going to do 0.05 divided by 12. So 0.05 divided by 12 is 0.0042. Yeah, I'm going to say that, 0.0042. It's actually 0.00416667. Actually, I'm going to do 0.00417 just to be a little tedious here. It's hard, like, me telling you to do that is kind of hard because you don't really know what you should round to. But I can kind of see here that this is going to trail off all the time, so that looks like a good spot for me to stop rounding. That really just comes with time. I've just been doing math too long. All right, so you get that. The next step is to add these two things. I think if I just backspace this, it'll add them. That should be 1.00417, all right. Then I'm going to raise that number, so I'm just going to hit plus 1 here. I'm going to leave this here, so I'm not even going to put in the 1.00417. I'm just going to hit plus 1 to show that that's plus 1, all right. And the next thing I want to do is raise that exponent, so I'm going to raise it to the 120th power. So I'm going to use this key, x to the y, raise it to the 120th power, which might seem like a lot. Like you might think, oh my god, it's going to be huge. And it is going to be a lot bigger than just 1, but it's not going to be terribly bigger. So it's 1.647. See, not that big, right? And then I'm going to multiply that by 1,000, because that's 1,000 on the outside. And that equals $1,647. So A equals $1,647, and we care about cents, right? Oh, it's only 1 cent. It's really not even that much cents. So that's how much is going to be at the account at the end of 10 years. All right? Now, if you think about it, if I put in $1,000 initially, I really only earned $647, if that makes sense, because that's all interest, which is actually really good. If you can get an account like that, that's pretty awesome. All right, let me do the next one for 20 years to show you the difference. Now, do you think that after 20 years, it would be double this since it's double the time there? So let's see. If I multiply that by 2, would it be $3,294? I think some people might think that because it's twice as many years, but you gotta think we're compounding. It's compounding is something totally different than just multiplying. So everything else here is the same, except for this part. So instead of 120, I'm doing 12 times 20 years. So it's 240, so I'm just doubling this. All right, so I'm going to work backwards again, just like I did before. I'll show you that. All right, so again, oh, well, shoot, guys, I don't have to do anything, right? Because I already know that that's 1.0047. So let me just put that in there again. 0.00417. Right? So I'm going to put them in my good old calculator. So 1.00417 to the... Did you hear me pause? I always make sure I put in the right number. I feel like sometimes students like just fly through these problems. You got to make sure you put in the right number. So I raise it to the 240th power, and then I multiply that by 1,000. And what do I get? Dun, 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 dun. $2,714.80. $2,714.80. Now, I asked you, would it be double that? No, it's not. It's not double. Just because it's double years doesn't mean that it's going to be double that amount. So no, it doesn't double. It's compounded. Compounding is much different than doubling. All right, now let's look at this last question here just to give you another idea. So this one says, suppose that 350 years ago, one of your ancestors deposited $1 into a savings account earning 6% interest compounded annually. That's just silly, right? I mean, like, first, are there banks that are that old? I guess so. I don't know. That's just kind of a silly problem. But it's worth looking at because it's kind of an interesting idea. So one of your ancestors deposited this much into account. But here's my key word that's different here. You see the word annually there? It's not monthly right now. It's annually. So it actually changes the formula. So here, instead of dividing by 12, you're thinking about how many times it compounds in a year. If it's monthly, it is 12. But if you're compounding annually, it just compounds once. So this actually just changes to a 1 here. So that's a little tricky, right? And sometimes you'll see these actually like compounded quarterly. Quarterly, that bottom number changes to 4 because there's 4 quarters in a year. You might see biannually. That would be twice. So you got to be careful there too. So let's just see for fun. So they put in $1. Your ancestor was so generous. They put in $1. And 6% interest. I guess back in the olden days, interest was high. All right, now here's our N. What's our N going to be? So they did it 350 years ago, and there's 12 months in a year, so multiply by 12. 4,200 months. That's a lot of months. All right. So 0.06 divided by 1, that's just going to be 0.06, right? So I really don't even need that divided by thing. So it's really just 1 plus 0.06. So let me just copy this again so that we can put it in our good old calculator. So 1 plus 0.06 equals 1.06. I raise that to the 4,200th power. Holy crap. Whoa. Okay, this is really cool. All right, and then I have to multiply by 1 on the outside, but y'all know if I multiply by 1, it's the same thing. All right, so I get this answer. It says 1.92, all these numbers, e to the 106. So what does that mean? So it's 1.9, I'm going to say 9.3 times 10 to the, let me get my equation editor again. Insert equation. So A equals 1.92 times, let's see, it's going to be 10 to the, what was that number? 106. You don't see that 10 to the 106 in my scientific calculator. They put an E. I don't know why calculators do this. They really, I mean, they're good enough now. I would think they could just put times 10 to the 106. But if you remember back to olden days, whenever you took math before, times 10 to the 106 is scientific notation, meaning that this would be 1 followed by 106 zeros. What would that even be? Let me just go to Google. Let's see. 1 with 106 zeros. What would that be? Sometimes Google helps. Nah, it doesn't have it. Because they have it like, there's a Google. Oh, here we go. Yeah, let's get Wikipedia. All right, let's see. So 10, what do we have here? 10 to the 106 power. So see, okay, so 10 to the 100th power is a Google. It's a Google. It's not like Google didn't name this. It's something it's a really large number. So you have 1 over, because you still have like 6 more zeros, and that's a billion. So 6. So if you have 6, oh, that's a million. Sorry, math teacher here. If you have 6 zeros, it's a million. So you have 1 Google and $1 million. That's a lot of darn money. If you happen upon this ancestor, help out your old math teacher here. That's pretty cool, huh? All right, so that's all I got for you. If you have any more questions, let me know. If you keep wanting me to make these videos, let me know. It seems like a couple people would help them out. But anyway, keep posting into the discussion boards. I'm enjoying reading your posts. Keep talking to each other. And otherwise, email me if you need me.